Hi, in this video I'm going to talk about this concept of interference and harmonics, okay? And we'll do a lot of demonstrations with this stuff in class, but for now I'm just going to talk about the theory and how to do the math. Okay, interference is basically, as you can see, is just two waves that are going to interfere, right? They're going to meet at some place, okay? And we're going to try to figure out what the outcome is. Now, in here, at least in this class, we're just going to look at total complete destruction or complete construction. In other words, they're going to kill each other or they're going to build on each other. So the picture here shows you complete or total constructive interference. The two waves meet, okay? They have the same frequency, right? And their amplitudes add up to give you a bigger amplitude. So that's constructive interference or full constructive interference. Complete destructive interference is when the crest of one meets with the trough of the other, and you end up with just an amplitude of 0. And there is everything in between. And we'll look at the special case when we talk about beats, right? We'll define what beats are and why they happen. Okay. Now, these two statements are extremely important here. It says if the difference in distance from the two sources to a certain point is a multiple of the wavelength, constructive interference occurs. We mean total constructive interference here. Basically, if you have a source S1 here and S2 here, and you have a certain point P here, okay? And you measure this distance, and you measure this distance. Let's say this is D1 and D2. Okay, D2 minus D1 in absolute value, we don't care. If that's going to be a multiple of a full wavelength, then you're going to have a full constructive interference. Because when they arrive there, they're going to arrive in phase. They're going to arrive just like this. So I hope you can see that. In other words, the crest will meet the crest or the trough will meet the trough, but they're going to be there at the same exact, when they get there at the same time, they're going to have a difference of a multiple of a wavelength. If the difference is a multiple of half a wave, okay, it means they're going to arrive like this. So I hope you can see that. They're going to arrive out of phase. That's when you're going to have complete destructive interference. And there are a lot of RTs that we're going to try, or you're going to try for homework, that will use this concept here. So keep that in mind. Now I'm going to jump a little bit and I'm going to go to standing waves, okay? And then we'll do some demonstrations and you're going to see it live. It should make some meaning once we do demonstrations. Okay. Now we're going to do a standing wave on a string. So if you take a string, like a guitar string for instance, okay, and it's tied at both ends, okay, and if you pluck the string, you're gonna create a pulse, right? When this pulse reaches the other end, because this end is being fixed, it's gonna bounce back inverted. Okay? So basically, in this length of the string, we're able to fit half a wave. So this is 1/2 a wave. You can have another scenario where you have a whole wave, okay? L equals, I know I'm going to do a demonstration with this, and I'm going to show you what it looks like. L equals, and we're going to do this in halves, 2 halves. You got a 1/2 here, you got another half to complete the wave. And here you get 3 halves, because everything is in terms of halves. And here you get 4 halves, but it's the same length of the string. Okay? And that's where this formula comes from. Okay? So I'll show you where that formula comes from. So V equals lambda times frequency. So we're going to try to solve for F. So F equals V over lambda. So F equals, the V is just the V. Now, here, if we try to solve for lambda here, it's just going to be 2L over 1. In here, it's going to be 2L over 2. Here, it's going to be 2L over 3. Okay, so this is basically going to be 2L over n. And n is the number of the harmonic. So fundamental is the first harmonic, second harmonic, which means n equals 2, etc., right? So if I move this n up here, so this n here, it just means frequency is as a function of n. So, and you can see clearly here that to go from one to the other, it just double the frequency. So the frequency here is twice as much as there. The frequency here is 3 times as much as there. Okay, so I think we can say that Fn is n times the fundamental. Okay, that's basically what it's saying here. F2 equals 2 F1, F3 equals 3 F1, etc., right? And n can take any number. There was no skipping because later on we're going to see that we're going to have to skip. Okay. So that's something for a string, meaning okay, it's tied at both ends. Now let's look at something that's a tube that's open at both ends. So if you have a tube that's open at both ends, okay, and actually before I continue with this, I want to go back to this. Okay, so the highest point here is called an antinode, and the point here is called a node. Okay, an antinode you have maximum energy, and the node you have no energy. So in other words, if you can touch just that single dot while the string is vibrating, you will not disturb this pattern here. All right, so let's look at something that's open at both ends. Okay, in order for it to be open at both ends, okay, you have to have an antinode at each end here, and the node is in the middle, right? Now, if you look at this, that's a quarter of a wave, okay? And this is another quarter. So basically, in this length here, you're able to fit half a wavelength, right? In order to get the next harmonic that's open at both ends, right? See, if you continue with this, assuming that you keep the length the same, you're going to close it here. So in order to get to the next one, you can't just add a quarter. A quarter will close it here. So you have to add 2 quarters so that it stays open at both ends. And if you can squeeze all of it inside here. So for the next one, L should be, you have half there, and you have to add another half. So you have 2 halves. And if you continue with the pattern, you're going to see that it follows the same rules as a string that's attached to both ends. So if something is open at both ends, or if it's tied at both ends, then Fn meaning like the frequency of the nth harmonic, follows this rule here. And I think I should add Fn equals n times F1, and n is basically, can take any positive integer. Okay, so the same rules apply. Now let's look at something that's open at one end and closed at the other. And we're going to do a lot of demonstrations here. You see that it's not too hard. Okay. In here, if in order for it to be closed at one end and open at the other, it has to look like this. Okay, so it has to be open here. So this is an antinode, this is a node. And between the antinode and the node, there is a quarter of a wavelength. Okay. For the next one, if you decide to go with another quarter, you're going to close it at this end, but it has to stay open. So you can't just add a quarter. You have to add 2 quarters, right? So which means you have to add a half. So for this one, I think we can say that L is equal to 1 quarter of a wave. In here, L is equal to not 2/4, but 3/4. And that's the trick. That's the difference between closed at both ends, open at both ends, or closed and open. The next one will be, I can see 1/4, 2/4, 3, 4, 5/4. Okay? So that's the skipping. And if you follow the same proof as before, you're going to come up with this formula here. Okay? But n skips. It's only integers. So which means Fn is equal to n F1, but n has to skip. In other words, you can't talk about the second harmonic. You have to jump to the third and the fifth and the seventh, etc. Right? And that's it for this. But there will be a lot of practice that we're gonna do with this. Okay. All right. Thank you.